My name's Brad. I'm going to be talking about GFXReconstruct, the suite of tools for capturing and replay and processing capture files. And I work for LunarG, so we got a kind of a long run today. I think I'm the last of LunarG people today. And thanks for coming. Today I'm going to go over what this thing is, the use cases for it, how to capture Vulkan command streams, replay those streams, and other tools that you can use. A little bit of the architecture, kind of depending on how interested people are, or whether they're falling asleep or heading for lunch. And I left live demo on here, but I'm not going to do that because that is problematic. How many people have used GFXReconstruct? Like a third, quarter? All right, good to know. If you did that, was it from the SDK? Not a lot, okay. Did you build it from source? More than I expect, good. Okay, so for those of you who didn't raise your hand, what this thing does is it captures Vulkan commands to a file. And then allows you to replay those commands essentially verbatim with some modifications. It contains a handful of additional tools for doing things like optimizing capture files, extracting shaders, changing that to text mode, and there's a few others that I'll mention as we go through the slides. Most of the source code is C++ with a couple of Python wrappers and Python scripts. It runs on Linux and Android and Windows, and it's API agnostic. The actual underlying framework, the structure, doesn't specify Vulkan, and so we now have a Direct3D 12 implementation, which I won't go into here, because that would be rude. What do you use this thing for? Well, its fundamental purpose is to record and play back as close to the original stream as possible. So the main use for it is driver regression testing or other regression testing frameworks. But you can also use it for playing back in an architecture simulation sense, like if you have a C model or an FPGA or some kind of a, it's not full silicon yet, or maybe it's actually silicon which is not fully integrated. You can take a capture of a running app, and you don't have to have the app in order to run the same Vulkan commands on a new piece of architecture. It's also useful for bug reporting. So if you have an application and you know you have a Vulkan bug, you can run the application, capture the trace, and then send it to a vendor. Okay, so we've talked a lot about layers today, so I'm not going to go too much more into this, except I will say you can use Vulkan Configurator, but there's also a Python script which allows you to capture directly, so you can do gfxrecon.py, capture Vulkan, and then give it VK-cube or whatever your application is. This is a little bit more difficult with applications, for example, through Steam. You may find that you actually have to set up layers and then separately run the application through whatever its launcher is. And at the lowest level, you can use VK instance layers to set up that GFXReconstruct layer directly. We hook all the 1.3 Vulkan function calls, the core ones, and many extensions. I think most KHR, some EXT, and then we have a handful of vendor extensions depending on what we need. Depending on what we've ascertained are very important extensions for applications. We capture most function inputs and outputs. If a function fails, then we don't store the outputs because those could be invalid, potentially junk. And the layer writes one block per call to the capture file compressed by default. This output's not stored in error return. There's an additional case for that, which is in the to call idiom, like enumerate, where you pass in, okay, I want to know how many of these things I'm going to get, then I'm going to call again to fill a buffer. We don't store the input data to that because that's overwritten. So we have special cases for the enumerate functions to not write that. So in the same vein as everyone else has been showing VK-config screenshots, here's how you can do it to get a frame capture with GFXReconstruct. The things that I'm pointing out here are, you can select frame capture. On the right side, you can specify a hotkey. And so what that means is when you launch your app, it will not capture, but will instead track state and not write it to a file until you hit the hotkey. Then it dumps all the current state out and then starts writing commands for all the frames it's displaying. And then you hit the hotkey again and it stops. And you can do this repeatedly. You get one capture file for each one of these runs for every time you start and stop with your hotkey. And in vkconfig, you click launch. In this one, I've got configured vkcube, fairly straightforward. And this is what the output of that looks like inside vkconfig. The part that I'm circling here is just how you get the file name so you can do more things to it, like replay it. Some other interesting bits in here. This is GFXReconstruct version 0916, which is part of Focal Ubuntu. I forget what the Focal whatever thing is, but so that's actually just part of the SDK that I installed from the Linergy site directly. Oh, another thing I want to point out is the name here is GFXRecon capture trim trigger, and the trigger means that I used a hotkey to trigger trimming and then stop it. So while capturing, I'm going to tell you some of the options that you can turn on to change the behavior. Apps can map memory, and then they can not unmap in the case of a staging buffer. I think we all have seen that. So in order for us to detect changes, we basically mprotect under Linux. We use, I think it's called virtual protect on Windows to mark pages for a mapped buffer read-only. So when an application changes those pages, we can save that off into the capture file, only what's been changed by default, and it's called PageGuard. Sometimes there are issues with PageGuard. We install a signal handler for segfault for this case, and some engines conflict with that. We have a few options that I'm not listing here for helping us either chain or overwrite the engine's signal handler. But if that doesn't work, you can turn on assisted if you know your app uses flush memory ranges, but not everybody does that. And then the fallback is unassisted, which is if you do a submit, it just writes all the buffers all the time, but that's usually impractically, it's usually not, it's too much information to be practical. Okay, so I've been talking about trimming. And so intuitively, you don't want to save every frame for an entire game. There's going to be a lot of splash screens. Sometimes you have all scenes you got to get through in order to save off something. This is true for almost any application. So you can use a hotkey, or you can specify through vkconfig or through an environment variable ranges of frames. This one specifies that we want frame 1, then we want frame 2, then we want frames 10 through 20. That's going to be 3 different capture files. And so the way this works is we capture everything in a data structure without writing it out up to the beginning of a range. So for all 3 of these, we're going to be keeping track of this data. And then when the range starts, we write that out as part of that frame. But we're conservative because we're writing the capture file out at the beginning and we don't know what something might need later. And I'll explain a little bit more later about how to optimize that case, because it's potentially a lot of stuff that the frames don't use. Once you have your capture, you can use info to tell you more information about it. In this case, the compression format is LZ4, which is, I think, the default. The total number of frames we captured is 50. It's vkcube, which requested Vulkan 1.1, and then probably asked for a bunch of extensions on top of that. It was, and for this particular case, it was on a Radeon 6700. Then I haven't listed, but there's more information at the end about other things like device memory allocation, bits and pieces of, there's a consumer, and I'll talk a little bit more about consumers later, that collects up this information and spits this out. All right, once you have your capture file, you can replay it. We try and replay by default as close to the original as possible. That's not, it's not always possible to do exactly the same function calls on not this laptop, but I have a Dell, and I imagine many of you have laptops that have a discrete GPU and an embedded GPU. And sometimes if you try and replay without specifying anything, it'll use the wrong GPU, which has different extensions, different behaviors. So you can do -- GPU and tell it which one you want, and we select the physical device from that number. On Android, at the moment, we only replay one chosen surface. Our experience has been that Android titles will use one surface for an introductory sequence, and then another surface for copyright screen, and then another surface for the actual gameplay. And that's all stored in one big capture file. So you can use surface index to choose the one you want to play. And that takes a little bit of experimentation. This is something we're working on. And while replaying, you can save all the screenshots or some range of screenshots. So I say we try to replay verbatim, and it's very difficult to get a capture to replay on some other device. But it is possible to some varying degrees if you add additional options. Memory alignment types, those are in particular trouble. So you can translate these things using the memory remap or realign or rebind. Remap is pretty straightforward, pretty high performance, but it doesn't catch a lot of cases. Rebind is probably your best bet if you actually want to completely change your memory allocations to match a replay device's attributes and characteristics. So what rebind does is if you allocate memory, if the application allocated memory, it defers that until it's used, till it's mapped or bound, and at that time calls the Vulkan memory allocator to completely reallocate this object with the device's parameters, with the replay device's parameters. We have a flag command line option called remove unsupported, and on capture, we record all the extensions that were requested. Not all of them are always used. And so on replay, on a very similar device, maybe even a different driver revision, the set of extensions might be slightly different. So we have this option for, okay, go query the replay device's extensions and then mask off the ones from the capture file, which we don't see, or in the replay file, which we don't see. An example of this is a little while ago, there was KHR ray tracing. It was a provisional extension. It was a single extension. And we had a whole bunch of captures which used it. They queried it, they asked for it, and then they didn't actually provide any of the function calls. So they asked for it and then didn't use it. And so now we have a bunch of these captures. But that extension was broken out, as many of you know, into 3 separate ones with different functionality. And so you can use remove unsupported to try and run a capture like that to replay a capture. And then if the application used an actual piece of the functionality, all bets are off. So during replay, you may actually get a different return result code. It actually might fail, or it might give you like event not ready, where it was actually ready on capture. So that'll be printed as a warning, but won't necessarily stop execution. But one case where that's important is allocation. So if in the case where you run on a slightly different device, the capture might have failed to allocate memory, and then that was okay, and the application tried again and did something different. But on replay, that allocation might succeed, and then that completely changes the memory allocation behavior. So to force the allocation behavior to be the same, you can say --SFA, and that says, if the memory allocation failed on capture, don't do it on replay. And finally, we're getting a little bit more in the weeds here about things that need to be done. Swap chain acquisition order, the indices of the images that you get are not always guaranteed to be the same order, even on the same GPU, especially in cases like immediate present mode or mailbox mode. Because all of the resources are bound, all the resources and pipelines are bound to the image that they're going to be rendered to. If they come back in acquisition order in a different way than they did on capture, then you could get just garbage or a black frame or something worse. So we've introduced recently a virtual swap chain, which changes the render passes to all to go to a virtual to a render target, which is just a texture, and then we choose the correct place to put that on present. This can be disabled, but in a lot of cases that just won't work. And finally, the kind of the Hail Mary, that's an American football term, thing that you can do if you really want a miracle is you can actually change the WSI calls that are made using --WSI. I choose, there's a bunch of different things you can do, but one of them is auto. So you can choose an automatic mode to say if you had a Linux capture and you really just want to try and run it on Windows, you can do this and it may work. I've had some success with this, and it's kind of crazy to take a Linux NVIDIA capture and replay it on Windows AMD. But of course, the more sophisticated the capture, the less likely it is that that'll work. Okay, in the case that we've taken a capture and we trimmed to a frame range, and there's a lot of stuff in our capture that we didn't actually need for those frames, we can run optimize, and that produces a new capture which doesn't contain any of the resources that weren't used. Here's an example of, I ran some sample from Sasha Williams' suite, and I've lost in time what that was. But after running optimize, the size reduced, I was able to reduce the size by 28%, which is not too bad, and also increase my frame rate. Of course, this is without VSync, but 18% improvement here for frame rate. So if you're going to be repeatedly playing back a capture, this is kind of important. If you're just doing some debugging and turning around a capture and replaying it, maybe you don't care, but if this is going to go into a suite for regression, it's a good idea to run optimize on it so that you reduce your storage and then also your suite runtime. Okay, I love this slide because it's basically garbage, but you can run convert to turn a capture file into JSON lines, which is totally unreadable, but it is parsable, and it's fairly compact. And the reason we chose this is it removes all the white space from this, so it's much smaller. But what you can do is run each of these lines in turn through JQ. Who here has used JQ? Wow, okay. So JQ is pretty cool. You can run JSON through it, including JSON lines, one line at a time, and it'll do things for you, like you can filter out and select fields, but if in the default case, all it will do is pretty print. So this previous line here, the very first one, which runs off the side of the screen, if you run it through JQ, you get this slightly nicer JSON, which is more or less possible to read. And it tells you, this header that's stored in the capture file tells you what the original source file was. It tells you the version of GFXRecon that convert was using, which in here is, I think, a private version that I built, so you can see the git hash. Another field, the very next field is an annotation, which tells you what the original tool was who made the capture, and it was capture. Gives you the timestamp, and it tells you the Vulkan version that was used. So the next few slides illustrate kind of a quickie debugging in an editor. Probably a better way to do this is to actually do a replay of a capture file through RenderDoc. That's your best bet for having really good debugging of a capture file. But if you just want to dump out some JSON, bring it into VI or whatever, and start looking through some stuff, here's the first Vulkan function that's actually in the capture file, which is create instance, of course. But my example for this case is you want to know something about the first call to bind image memory. So here's a case where you can see the devices, each of these handles for the device and the image and the memory are indices that are stored in the capture file that are not related to the original. They're only mapped to the original handles from capture, but they are all maintained throughout the file. So if I see here image 23 and memory 24, I want to go see what image 23 was. So then I can just search for that. And I probably should not be using VI anymore, but there it is. And if you search for that, you get this. So this is the actual create image, which is earlier in the file, which actually created that image. And you can see that it was D16 depth format, 500 by 500. So this is the depth buffer for our VK cube run. Some other tools in the package include compress. Captures are compressed by default, but sometimes it's useful to decompress them or change compression types. And we have a special mode called extract, which removes all of the shader blobs from a capture file and sticks them in a subdirectory. And this is most useful if you want to disassemble those and look at them, or potentially make new shaders and substitute them on replay. So if you want to change something so it doesn't do anything, it just does a pass-through, you could do that here and observe the performance difference. When I originally gave this presentation several months ago, I went into some detail about the file format, but that's really not that important. What's really important is that we provide a whole bunch of classes and tools for reading and writing these file formats. The preferred way for anybody to process a file on their own is to subclass a thing called a consumer, and that gets called by us with all the parameters for the function that's of interest, and I'll show a little bit more of that later. But the short of this is that the file contains a header, and then it has meta commands and Vulkan function calls and now GX12 calls stored throughout the file one by one. So these are some of the components that are in the source tree. Vulkan Capture Manager is subclass from Capture Manager, and it does all the work of dealing with the specifics of capturing and then handing off Vulkan function calls for encoding and saving to a file. It also manages trimming, so it knows when to start and stop trimming. The encoder knows how to serialize an API call. So the encoder gets called with all the parameters for a function call, a Vulkan function call, and it knows how to stick those in a buffer. The file processor on the other side for replay knows how to read blocks that are from a file, which are in these buffers, decompress those buffers, and then call the decoders. The decoders know how to take a buffer and turn it back into these Vulkan function call parameters. So the decoder doesn't know what to do with it. It just knows how to turn them back into parameters. So the consumer will then take that and do something. The most common one that people run is Vulkan Replay Consumer. That's part of the replay tool. And so this process is you get a block from a file, you uncompress it, you decode it into parameters, and the Vulkan Replay Consumer knows how to actually call Vulkan to do that job. The Vulkan Stats Consumer gives us the info information that I showed on a slide earlier. I don't want to get too much into detail here, but I did want to point out one thing about this source code structure. If you look at it, we have a lot of generated code, but we don't generate that code at build time. We generate it when we think that we need to redo it for a header change, and then we check that code into the tree. And the reason we do that is that sometimes structures have changed in the past. And that's problematic because we don't have any indication of what's changed or what the structure's version number was or anything. So it's important for us to do that process by hand so we can see when errors crop up, and then we can figure out what to do with it. These slides will be available, so I'm not going to go into these, but you can go back and look at this. Okay, who wants me to go into a little bit more detail about what's actually going on in this layer? Not a lot. Okay. Who wants me to skip over these slides? No one? Okay. All right, I'll just go through these. I'll try not to go too deep. If you go looking in the source code, what you'll see is that we have a function called createImageView in encoding, and that's what is actually in the layer that gets called by the application when the layer is in the chain. And then we call down chain in the middle of our processing, and that's either the next layer or it's the implementation itself, which actually calls createImageView. And this is in Capture. Once we've called that function, so to back up a step, here I've got two constants, kmode track and kmode write. If you have asked to trim a frame range, like you've set the frame range to be frames 100 to 105, but you're not there yet. We're still drawing the frames before. We're in kmode track. This is just a bit field you can see in the source code. And so that just means collect up. So we're just adding entries to a state tracker. Then when we enter the frame range, we write all that out and we enter kmode write, which actually takes each function call that's part of the frame range that we care about, creates a call block object, which is basically just a chunk of memory, compresses that, and then stores it in the capture file. On replay, the reverse process, we read out one of these blocks from the file. We optionally decompress it, pass it through this series of from the file processor to the decoder, which knows how to just take these things out of a buffer and make actual variables out of them, and then calls each consumer in turn, which then actually does on replay the calls to the function that we want. To close out, we have a lot of future work on our hands. I have a spreadsheet of, I think, 65 features that need to be added at some point. So we do a lot of client work, and that dictates the priority for some of those things. And other times we have a little bit of extra time. We try and do stuff that we think is important for everyone else. We also do look at the GitHub repo issues and PRs. As we have priority, we try and prioritize them. We ask, we do have to take time to review each of those to make sure it fits into the source code style and so forth. I had Vulkan video on here was the next thing to do, but that got merged yesterday. So that's pretty cool. VKD3D Proton is pretty high on our list because Steam Deck. And recently we got a bug about sparse residency and sparse textures, which seems pretty important. So we're gonna look at that too, but I could just have pages of these. There's plenty of stuff to do. There's plenty of things in Vulkan that would be great, like looping frame ranges. We don't have that yet, but really want to add that so you can replay everything up to a frame range and then just loop that really quickly. But that requires a lot of intelligence because you have to rewind and tear down objects and create them again and so forth. Okay, with that said, yeah, you know the drill. So here's the repo link again, and my email address if you have any questions. On the right-hand side is that SurveyMonkey link again. On the left side is this presentation, but I've changed it this morning. So probably the best thing to do is look at that QR code tomorrow. And looks like I have time for some questions. And then we're going to have early lunch, I guess. Go ahead.
Does RenderDoc also use this for the frame capturing?
The question is, does RenderDoc use this for frame capture? The answer is RenderDoc does its own thing. We've talked from time to time. It's a, no one wants to step on Balder's toes. He's doing a lot of work. But one thing we've talked about is making a prototype, which would use these captures and could read them into RenderDoc. The simpler version to do that is just to capture with these tools and then replay with RenderDoc enabled, and that sort of gives you the poor person's version of that. More questions?
What's missing for VKD3D Proton?
What's missing for VKD3D Proton? I think mostly it's extensions that were added as part of to support the layer. I think we have a couple of things like there's a mutable a descriptor update extension or something that allows you to pass in host memory. So we don't do that. I think right now we just say we block that on capture. So it turns out it works. That extension is used as an optimization. So it's okay, but we really would like to support that. I think there's a handful of others that are pretty obvious in the issues list on GitHub. VKD3D, just VKD3D really. The thing that turns T3D12 into Vulkan.
It's actually called VKD3D Proton.
Okay, yeah.
That's the name of
The full suite.
So it's not the same thing as Proton.
It's not the same thing as Proton, okay.
It's just a part. So you're capturing the Vulkan part.
We're capturing, well, yeah, we're capturing the Vulkan part after VKD3D Proton has created Vulkan function calls from the DX12 calls. If I have this right. I always mix up VKD3D Proton and DXVK. Okay, thanks. And so yes, it's the Vulkan calls after translation. Sure.
Or like what's the use case?
Yeah. If you had a suite of machines and potentially driver revisions that you wanted to be testing in a farm, this would be a use case for that. That's the use case for this. You can take a bunch of captures and then you can do them and replay them automatically. We have a farm that does this. This is for our code quality purposes, but whenever we make a change, it goes to the farm, does a bunch of replay on a bunch of different machines, and then does a golden image comparison. So it's more for that. If you want to do debugging, RenderDoc probably is the better tool, where you actually want to look at the contents of a frame, click through things, look at textures, look at what the actual draw calls were. So it's really for the other thing. Oh yeah, also this, you could potentially have the entire suite of frames for whatever you're looking at. Usually people want to shrink it so their test suite's faster, but I think RenderDoc's only one frame at a time, right? Yeah. And yeah, the statement is it's easier to consume graphics. We can start traces for testing, for regressions, fewer clicks, fewer having to deal with things. There's also less that you can do. I mean, RenderDoc gives you a lot more that you can do. So those are the trade-offs.
What's the contribution policy? Because back in the day, a year ago, I've been a merge question.
That's yours. Yes. Right. We actually we used it. We actually used it as the template for a new one. That one. Right. So one of the things was that was pretty early on, right? It was a beta version. Yeah. Right. So you provided the PR, the initial PR for the beta video extensions, and that was really great. It did actually give us something to work from, and so I really appreciate that. And I'm sorry I didn't clarify that you had that. Yes, thank you very much.